solution and session chair for spin transport and dynamics in antiferromagnets. And I guess we can start off with our invited speaker, Jiaming He. And he's going to talk about the vector Spin Seebeck effect in antiferromagnet with canted moments.
All right. Hey. Good morning, everyone. My name is Jiaming He from University of Texas at Austin. I'm a fifth-year PhD student at Professor Jian Shizhou's group. And today I'm going to represent our collaborative team to talk about vector spin Seebeck effect in antiferromagnet lutetium ferrite with canted moments. I will begin by a brief introduction to the spin Seebeck effect, the generation of spin current, the detection of thermal voltage, and I will also go through some typical measurement configurations as well. Then I will talk about the spin Seebeck effect in the collinear ferromagnetic and collinear antiferromagnetic insulators. I will talk about their magnetic structures, the measurement configurations, and the signal detected. Then I will talk about the non-collinear canted magnetic structure of antiferromagnetic insulator lutetium ferrite, and along with the vector spin Seebeck effect that we observed in the lutetium ferrite with heavy metal overlayer. And we will show that the thermal voltage that we detected are intimately connected to the off-axis magnetization, and we want to show that the transverse spin Seebeck effect that we surprisingly observe in this material has shown some evidence of spin swapping effects happening across the interface of lutetium ferrite and tungsten. And finally, I will do a summary. Okay, let's first talk about the spin Seebeck effect. Since this was first experimentally observed by Dr. Uchida and Dr. Saito, it galvanized the entire spin color-electronics community with a lot of interesting results in the past 15 years. And here we show a typical schematic of spin Seebeck effect device. It consists of three crucial parts: the magnetic insulator layer, the metallic film, and the temperature gradient. And here you can see that the magnetic field is applied along the x-axis here. And with an out-of-plane temperature gradient, a spin current is generated inside of the magnetic insulator layer and injected into the heavy metal film and converted into the voltage by inverse spin Hall effect and being picked up by a voltage probe along the y direction. And this can be given by this relationship here. And from this relationship, you can see that this inverse spin Hall voltage, the spin polarization index, the spin index, which is parallel to the magnetization, and the spin currents directions are mutually perpendicular to each other. And also, in this magnetic insulator, the magnetic moments are following the field direction. So, apart from the mutually perpendicular relationship, with a metallic film overlayer, you can only detect the spin current injected from the out-of-plane directions. So that's a brief rundown of the spin Seebeck effect, the mutually perpendicular relationship, the out-of-plane spin current detection. Now let's take a look at the spin Seebeck effect in the ferromagnetic insulator. And a typical system would be like yttrium iron garnet with platinum overlayer. And this is reported by Dr. Saito back in 2013. And let's see on the left-hand side, we have the same configurations as we showed before. Here, the magnetic field is applied in in-plane x direction, which aligns the moment along that direction. With out-of-plane temperature gradient, a spin current is generated and injected into the heavy metal layer. And with a voltage probe along the y direction, there's a microvolt range of signal that's pretty clear here. However, in the yttrium iron garnet with platinum overlayer, if you switch the temperature gradient direction from the out-of-plane along z to in-plane along x, and you still maintain the mutually perpendicular relationship, which sets the moment and magnetic field and the spin index along the z direction, and the temperature gradient is along the x direction, With a y direction applied voltage probe, there is no signal. So this is the transverse spin Seebeck effect measurement configurations. And here, with the in-plane temperature gradient, the spin current directions is in plane. And with this metal overlayer, you cannot see any signal. So this tells us for the ferromagnetic insulator, only vertical temperature gradients inject a detectable spin current in this type of material. All right, let's take a look at another case, which is Spin Seebeck effect in antiferromagnetic insulator. And here we have chromium oxide with platinum overlayer, and this was reported by Takura group back in 2015. And they use a chromium oxide single crystal that they grow with floating zone, and they apply the magnetic field along the c-axis direction. And in this directions, the moments at LuFeO region, the moments are antiferromagnetically paired to each other. It cancels out. There's no net moment along the field directions at LuFeO region. So with out of plane applied temperature gradient in setup A here, which is longitudinal spin Seebeck effect setup, there's no signal. However, chromium oxide, if you apply the magnetic field along c-axis above certain threshold, which is 6 Tesla, the spin flop field of this material, the moment will gradually switch almost 90 degrees, not fully collinear. They have a slight canting towards the field direction, and this gives us a net moment in plane. And this in-plane moment with the out-of-plane applied temperature gradient, you can observe spin Seebeck effects. Just here, you can see that above 6 Tesla, there's an upturn of the thermal voltage detected. However, again, if you switch the temperature gradient from the out-of-plane directions into the in-plane directions, and you still apply the magnetic field along the c-axis, you can still induce spin flop transition with these configurations. So there's a switch out of crystal direction here, field along the c-axis, and even above the spin flop field, which is 6 Tesla, if with an in-plane applied temperature gradient, you cannot see any thermal voltage signal. And this is the case for the antiferromagnetic insulator. There's no spin Seebeck effect if you don't use a Tesla scale field to induce a spin flop transition and induce a moment. And also, again, just like the ferromagnetic insulator YAG with platinum, only vertical temperature gradient injects a detectable spin current. So they are pretty similar here. So this is the antiferromagnetic insulator case. Okay, before we move on to the lutetium ferrite result, we wanted to show you our measurement configurations, which we think is crucial because this allows us to apply temperature gradient uniformly in plane and out of plane directions. And we use a yttrium iron garnet with tungsten overlayer as a benchmark material to just do the measurement with this setup and compare it with previous studies. So on the left-hand side, it is the longitudinal spin Seebeck effect again. A piece of crystal is sandwiched between two pieces of copper block. The top piece have a heater attached to it, and the bottom piece is served at a heat sink. And here we apply the magnetic field along the y direction, which sets the moment and spin index directions, and we measure the voltage along both x and y directions. And we apply the temperature gradient out of plane, and we see a maximize of the signal along the x direction. And if you switch the voltage probe to the y direction, because it's parallel to the moment and spin index, there's no signal. And for the transverse spin Seebeck effect setup, it is crucial that there's no unintended out-of-plane temperature gradient that will give you a parasitic, like longitudinal spin Seebeck effect signal. So we clamp the sample on both ends with solid copper and with good thermal contact between the sample and the copper. One side have a heater attached to it again, and the other side is heat sink. and the heater side is thermally insulated between the heater side and substrate. And here you see we have a in-plane applied temperature gradient, and we have out-of-plane magnetic field and gradually switching in-plane directions, and we don't see any thermal voltage, and this is consistent with previous Yag and platinum Yag or tungsten results. And I also wanted to talk about the y-axis that we use here. You may notice that we are using a normalized voltage here because the sample, that oriented single crystal sample that we have are all disc shapes. They have different dimensions, in-plane and out-of-plane directions. In order to compare the results, like numerically between the two setup, we think it's necessary to normalize the voltage with regard of the temperature gradient and sample dimensions. All right, so Spin Seebeck effect is pretty common in the magnetic insulator like yttrium iron garnet, and we wanted to talk a little bit about the magnetic structure of yttrium iron garnet. And here on the left-hand side, we have a unit cell of Yag, and this is kind of like a strange looking, but the octahedra iron 3 the iron 3+ have like two different coordinations between its nearby oxygens, the tetrahedra and octahedra site. So the octahedra site have iron center is colored in blue, and tetrahedra sites are colored in yellow. So for each unit formula, which is just a unit formula of this Yag, we have 5 iron 3+. And the tetrahedra sites and octahedra sites are antiferromagnetically paired to each other if they're neighbors because of the exchange interactions. So each formula unit, we have 5 ions. There are 2 tetrahedral ion antiferromagnetically paired with 2 octahedra ions, and which leaves 1 tetrahedral site uncompensated, and that gave us a 5 Bohr magneton per unit formula, and that's a ferrimagnetic moment in the yttrium iron garnet. And this moment follows the field directions, so you can point field to any directions, and the moment will follow suit. And the Spin Seebeck effect we saw are coming from this moment. So this is the ferrimagnetic structure of Yag. But the magnetic structure for the lutetium ferrite is very, very different. And here we show a schematic of magnetic structure of Yag. Again, we have iron 3+, and iron 3+ is octahedrali coordinated with nearby oxygen. And the blue arrows here are a portrayal of the spin directions. And you can see that in the in-plane directions, in AB plane, the moments are antiferromagnetically paired to each other, and there's a slight canting towards the c-axis directions. And the neo temperature is 620 Kelvin in this material. And this canting is from Dzyaloshinskii-Moria interaction, or single ion anisotropy from the tilting of the octahedra. And it's intrinsic and it exists without externally applied magnetic field. So, the magnetization of this material, you can see that if you measure the magnetization of this material with field applied to c-axis, first, the moment along c-axis will exist without magnetic field because it's coming from the spontaneous canting. And the moment along the AB plane, because of the antiferromagnetically paired in plane, they're going to start with 0, and it will be much, much smaller than the spontaneous canting moment. And that's why we did the vector VSM measurement for the lutetium ferrite. And here, in the middle part, we have a field applied along the c-axis. And we monitor the magnetization along all 3 directions. And here you can see that even when there's no field, the field is 0, you can still see a moment along the c-axis almost saturating, and it's around 0.052 Bohr magneton, and that's roughly 1% of a full iron moment. and roughly 1% of the Yig moment. And this canted moment does not really follow the field directions, and the moments in plane in the x and y directions are much, much smaller than the spontaneous canting moment. The moment can also be flipped if you switch sign of the magnetic field. If you apply the field around a certain threshold, which is 150 Oersted along the c-axis, you can switch the canting direction from plus c to minus c. And if you apply the magnetic field in plane, so on the right-hand side, we have an experiment where we apply the magnetic field in plane and monitor the magnetization in all three directions. And here you can see even when you apply the magnetic field in plane, the spontaneous canting moment still dominates the magnetization in this material. And the magnitude of the spontaneous canting moment is still pretty much the same as the middle part. The moment along x and y directions are still pretty small compared to the spontaneous canting moment. This is pretty much the same as the magnetization if you apply the field along the z-axis. However, there's one difference. The difference is the switching field. This is up from 150 Oersted to around 1,000 Oersted. And this is because the only field applied along the c-axis can flip the spontaneous canting moment. And that's why we will just, from now on, we'll apply the field along the c-axis for this material measurement. Sorry. So yeah, this is the magnetic structure of the lutetium ferrite, and comparing to the collinear ferromagnetic Yig is quite different. It's different in a way that it has a much smaller, only 1% of the Yig full moment of from the spontaneous canting. The canting moment does not follow the field direction, but field along the c-axis can flip the moment, and there's finite moment at zero field. Okay, now let's take a look at Spin Seebeck effect measurement on the C-oriented lutetium ferrite with tungsten overlayer. And this experiment is done with the same setup as previously shown, Yig and tungsten. And here, we apply the temperature gradient out of plane. We apply the magnetic field along the c-axis as well. And we monitor the voltage in x and y direction. And surprisingly, we saw voltage in both directions, as opposed to Yig. If you apply the voltage probe along the moment and spin index direction, you don't see any signal. But here we saw signal in both directions. The signal resembles very well with vector VSM data in a way that at zero field, you can still see finite thermal voltage. And the voltage can be flipped by a small amount, which is around 150 Oersted of magnetic field. And the voltage magnitude along x and y direction are pretty similar to each other. And this is pretty interesting for the longitudinal Spin Seebeck effect data. What's more surprising is the transverse Spin Seebeck effect data. And here, we switch the temperature gradient from out-of-plane direction into the in-plane directions. And there's no thermal voltage in collinear ferromagnet and antiferromagnetic insulators. But we saw signal in both x and y directions. And this signal that we observed, again, still resembles pretty well with the vector VSM data. They are pretty similar in the magnitude, exists without magnetic field, and can be flipped by a small amount of magnetic field. And that's pretty surprising to us. So now let's do a side-by-side comparison between the longitudinal Spin Seebeck effect and transverse Spin Seebeck effect. And here, not only we saw a signal on the transverse Spin Seebeck effect, this signal is 10 times larger than the longitudinal Spin Seebeck effect setup. And again, we normalize the voltage so that we can compare them together. So the temperature gradient and the sample dimension are considered in this comparison. And we can establish a vector spin Seebeck effect relationship between the detected thermal voltage, the temperature gradient, and the magnetization. So here, the longitudinal spin Seebeck effect, we have out-of-plane temperature gradient. We think the thermal voltage is, can be attributed to the moment in the in-plane x and y directions. And with the transverse spin Seebeck effect setup, in-plane temperature gradient, we think the moment can be attributed to the out-of-plane magnetization, which is from the spontaneous canting moment. And out-of-plane moments are much larger than the in-plane x and y moment. So that's why the thermal voltage is larger. The in-plane x and y have a smaller moment and will give rise to a smaller thermal voltage. So that's why we call it the vector spin Seebeck effect. So it's vectorized in a way that both in-plane and out-of-plane temperature gradient can generate spin current and can be picked up by inverse spin Hall effect voltage. And the voltage signal is proportional to the magnetization of this moment. And here we can see that we essentially can use spin Seebeck effect thermal voltage to probe the small magnetization in this material. All right, we kind of attributed the thermal voltage to the corresponding component of the magnetization in this material. And there are further verification measurements that we need to do to bolster this claim. So here, again, as transverse spin Seebeck effect setup, we attributed voltage to the spontaneous canting moment along the z-axis. And we designed an experiment that mark the sample in the corner and rotate the sample 180 degrees along the z-axis. So the moment, for the transverse spin Seebeck effect, the moment is from z. If you rotate sample this way, it does not change sign. And if you measure the thermal voltage, we're not expecting to see a change of sign of the thermal voltage. And that's indeed what we observed here. And for the longitudinal spin Seebeck effect, we attributed the moment to the in-plane x and y component of the magnetization. And again, we marked the sample in the corner and rotated 180 degrees. And if the thermal voltage is from the in-plane moment, if you rotate sample this way, you're actually expecting to see a change of sign of the thermal voltage detected. And that's indeed what we have observed here. So, and this is the verification measurement to make sure that our attribution of the thermal voltage is correct. Also, we wanted to do more verification measurement to address some of our concerns. We have two main questions here. The first question is the voltage mainly from the inverse spin Hall effect? And before we show a inverse spin Hall effect relationship, the equation here, and we show it again here. Now we play with the spin Hall angle in this equation by proposing a experiment modification, replacing the tungsten overlayer, tungsten have negative spin Hall angle, to the platinum overlayer, platinum have positive spin Hall angle. So if you change sign of this spin Hall term, you're expecting to see a change of sign of the thermal voltage detected. And that's one of the experiment modification that we're gonna do. And the second question is there any magnetic proximity effect in the platinum? Because when platinum is contact to a magnetic insulator, there is a possibility that there will be induced moment within the platinum, and with an out-of-plane temperature gradient, there might be anomalous Nernst effect. So the anomalous Nernst effect have the same measurement configuration as the spin Seebeck effect, and we wanted to make sure that our signal is not dominated by the anomalous Nernst effect. And we proposed the experiment modification by inserting a non-magnetic copper layer between the tungsten and lutetium ferrite. And we wanted to test the signal again and see if the signal is preserved. If the signal is mainly contributing from anomalous inertia effect, you should expect the signal to fully disappear. With that said, I show the result of our modification measurements. And all of the modification measurements are like, the modifications are applied to all of our measurement configurations. So for the first question, if you switch the metal overlayer from tungsten to platinum, and they have opposite spin Hall angle, we are expecting an opposite sign of the thermal voltage, and that's indeed what we observed here. And this tells us the thermal voltage we observed is mainly from the inverse spin Hall angle. And for the second question, are there any possible magnetic proximity effects in platinum? Namely, are the signal is mainly from the anomalous inertia effect with a non-magnetic copper buffer layer between the tungsten and lutetium ferrite? The signal is still preserved, and that tells us the Spin Seebeck effect contributed to the thermal voltage that we observed here. Okay, so now there is one question that lingers. We have observed a transverse Spin Seebeck effect in the non-collinear canted moment in the lutetium ferrite, and this is not observed in other collinear ferromagnetic and antiferromagnetic insulators. And what is the origin of this thermal voltage that we observed? And yeah, we have in-plane applied temperature gradient. We can, so the experimental observation was we apply an in-plane temperature gradient. We drive a spin current along the y direction with a spin index along the z direction. And in the heavy metal layer, we have detected pick up a spin current along the z directions with spin index along the y direction. And this is our experimental observations. And this is pretty similar to the previously proposed spin swapping mechanism by Lifshitz and Dynakov back in 2009. And in this paper, they talk about the possibility of the spin current and spin index being interchanged across the interface. And of course, we're working with our theoretical collaborators to further investigate the details of the spin swapping mechanism across the interface. All right, so far, we have only showed the Spin Seebeck effect measurement with a C-oriented crystal. So the canting moment is always along the z-axis. And also the spin index moment direction is always along the z-axis. What if the spin index is in plane? What if we have we switch the canting moment from out of plane to the in plane directions? This is a recent experiment that we have done with a piece of A-oriented lutetium ferrite crystal. And so the A-axis is along the z-axis, and the canting moment is somewhere in plane. With the out of plane, and we did longitudinal and transverse Spin Seebeck measurement on this device, and with the out of plane temperature gradient, we apply magnetic field in plane along x directions, and we probe the voltage along the y directions. And here, we have an in plane moment with an out of plane temperature gradient, and we picked up a voltage along the y direction, mutually perpendicular, and the spin index, spin current direction is from the spin current direction is from magnetic insulator into the heavy metal layer, and this is very similar to the Spin Seebeck effect people observed and reported in the Yag and platinum, and this is expected. And we did indeed see a signal. And the signal still exists without magnetic field and can be switched by a small amount of field. And the switching field is slightly larger here because we apply the field not exactly along the z-axis directions, so a component of field can act as a switching field. For the transverse spin Seebeck effect measurement, we applied the temperature gradient in plane, and here we also applied the magnetic field in plane. The canting moment is in plane, the temperature gradient is in plane, and so the spin index direction and the spin current directions are both in plane. They are perpendicular, but they're both in plane. Even with spin swapping that we proposed before, the swapped direction will still remain in plane and will not be able to pick up by a voltage probe along the metal overlayer. And we're not expecting to see any spin Seebeck effect signal. And this is what we have observed as well. All right, so let's do a summary. We have observed a vector spin Seebeck effect in the lutetium ferrite, which is a non-collinear canted magnetic insulator. And both in-plane and out-of-plane temperature gradient can inject spin current in all directions in the lutetium ferrite. And we also observed that the spin Seebeck effect is proportional to the off-axis magnetization. And the transverse spin Seebeck effect we uniquely observed is consistent with previously proposed spin swapping effects. And also, in other rare earth ferrite, rare earth perovskites, such as lanthanum ferrite, lanthanum is on the other side of the periodic table of the SI rare earth element. We tested that and exhibit very similar spin Seebeck effect as well. And a very interesting experiment that we might do in the future is like play with ionic radius and spin canting angle. Because if you change the size of the A site, the ionic radius, you will be able to play with the spin canting angle, and that will give you a different amount of moment, and the magnitude of the moment might be related to the thermal voltage you detected, and that will be a pretty interesting experiment to do. So yeah, we have seen the very similar spin Seebeck effect in other rare earth perovskites. And just if you're interested in that part of the result, we have a virtual March meeting talk that is happening in a later date, and the time and the information are here. And Professor Weiwei Lin from Southeast University in China is going to talk about the spin Seebeck effect in the lanthanum ferrite, and he will delve into the detailed explanations of the spin swapping mechanism as well. Okay, so this has been a collaboration between Johns Hopkins University, University of Texas at Austin, and National Taiwan University. And we are grateful for the support from Department of Energy, National Science Foundation, and Ministry of Science and Technology in Taiwan. Thank you so much.
Temperature gradient across the magnetic insulator, or is it because of the temperature difference between the magnetic insulator and the metal?
That is a very good question, and I myself also wonder that. I kind of put in some proposal to the Argonne National Lab to probe the interfacial magnetic structure and see if it's any different between the bulk magnetic structure. And as you know, the Argonne is shutting down in the coming April. So this is planned experiment, and I hope I can find the answer in the future. Yes, I actually have a slide to show that. Okay, so if you move around the voltage probe when you're doing the transverse spin Seebeck effect measurement, we see that the thermal voltage that we observed is largely remain unchanged, and that's a way of like proving that the temperature gradient that we applied in plane is pretty uniform across our samples. Thank you for the question.
Very short question. These matters either precise geometry,
Mm-hmm.
either orthogonal phase or hexagonal phase. In your case,
In our case, we're orthorhombic phase. So yeah, the hexagonal is different, and I've seen a lot of thin film growth of the lutetium ferrite in the hexagonal phase. Oh, my sample are just like bulk single crystal from, and it's a couple of millimeters in thickness, and it's 5 to 10 millimeter in the in-plane dimensions. Yes, this is a very insulating material. I'm sorry? Yes, I'm aware of that. And as I said, we are still trying to figure out whether if this is spin swapping. We've seen some evidence of it from our experimental observation, but what exactly is happening, I think we need more experiment and to figure out that.
So I think we should move on to the next one. And let's think about
Thank you.